Hello everyone. So now we're at the point where we're ready to kind of go for the whole degree of this unit and trying to figure out the polarity of a whole molecule. And the parameter of the molecular polarity is of vital importance. And as later on we're going to discuss. And that overall polarity of the molecule dictates interaction between the molecules, and hence solubility, the miscibility between liquids, solubility of solids, all plays into a very, very important role. And we have to start talking about molecular polarity to revisit what we call it polarity for individual bond. Excuse me. So for polarity of individual bond, as we learned previously, when molecules such as hydrogen are formed, the best way for hydrogen atom to do is to share this pair of valence electrons to form a covalent bond, and this is a covalent bond. And as you can see, the attraction of the hydrogen nucleus towards this pair of shared valence electrons are equal because they are the same, so there is hardly any difference. So this one has to be reside right in the middle, shared equally between those two hydrogen atoms. So hence for the hydrogen, and there's no partial charge because there's no preferred location of this shared of this pair of shared valence electrons. So we end up with this is nonpolar. When you examine the one particular bond formed between hydrogen and oxygen in water, and as you can see, the pair of electrons is much closer to oxygen as compared to hydrogen. In this case, it's because there's a large difference in electronegativity. Oxygen has a higher electronegativity compared to hydrogen, so the pair of valence electron share between those two is leaning towards, is getting closer to the oxygen atom, and it's getting away slightly away from the hydrogen atom, so you impart a slightly negative on the oxygen atom and slightly positive on the hydrogen, and also on this side it is slightly negative on oxygen, slightly positive on the hydrogen. So this is actually called polar covalent bond. So this is actually called a polar covalent bond. So then we will have a slight notation for that. You always an arrow pointing towards from the positive towards the negative, from the positive towards the negative, and this is a kind of polarity. The arrow is from positive to slightly positive, slightly negative, and the size of the arrow will indicating how large the difference in how large the polarity. And now you actually see, we just do a quick review when what we call the difference between electronegativity. En stands for electronegativity, delta means the difference. If it's kind of less than 0.3, and this is you have non-polar covalent. So if it's between 0.3 and 1.0, This is called slightly polar. Hopefully you recall that information. It is crucially important you retain the useful information from the previous units. And if it's between 1.0 and 1.7, now we're into the realm of polar covalent. So this is slightly polar covalent, and this is polar covalent. If the electronegativity difference is big enough, and now we're going to have a complete transfer of valence electrons, hence ionic compound. So this one is going to be ionic. Excuse me. So this one will be ionic. So those are talked about. We talked about the individual bond, and now how we're going to actually add those individual bonds together in molecule. We determine the overall polarity of the molecule. So how do we do that? So here is the kind of the protocol for identifying the polarity of a whole molecule. So the first step is you determine the polarity of individual bond. If the individual bond is nonpolar, covalent, which means they do not have much of a difference in electronegativity, the whole molecule is nonpolar to start with, because if you have a nonpolar bond, doesn't matter how many you have, you add all of them up, doesn't matter how you add all of them up, you're going to have nonpolar. So the whole molecule will be nonpolar. So if the individual bonds are polar, which means they are the electronegativity difference is greater than 0.3, then we have to go through the proper steps to obtain the molecular geometry using the Vesper theory. Remember the steps: you count the valence electrons, and then you get the central atom, and then you go through the steps to get the Lewis structure. Then you get the electron group geometry. Then you get A, B, X, E, Y notation. Then you get the total number of electron groups. Then you get the electron group geometry, and then from there to see how many electron groups are actually connected with the atom. So you got the molecular geometry. So this is the whole process for everything's based on the valence shell. Electron pairs, they strongly repel each other. So this is the Vesper theory. So then now you use that molecular shape of the molecule, and now you have to add each polar bonds in three-dimensional space. This step is going to be the most challenging one. You have to treat each polar bond as a vector with arrow pointing from the element with lower electronegativity towards the one with a higher electronegativity, where you're pointing from the slightly positively charged end towards the slightly negatively charged end. Now, this is the indication of the existence of polarity. The length of the arrow will indicate the magnitude of separation of shared valence electrons. So then you have to add them up in three-dimensional space. If the net polarity means you add up all those polar bonds, it's not zero, so the whole molecule is polar. Means the whole molecule have an even distribution of valence electrons. On one end, you'll have more of the valence electrons, so it's in part slightly negative charge. On the other hand, you will have less less valence electrons, so it will be slightly positive, and you will have an arrow. for the whole molecule pointing from one end to the other. So if the net polarity is 0, and as indicated in the next several slides, you can actually see the polar bonds, actually they can cancel each other out. The molecule is non-polar. So those are the steps one has to take to figure out the polarity of a whole molecule. Now let's take like some detailed cases. And if you have two electron groups, and both of them are connected with atoms, and this is actually cut and paste from the University of Colorado simulation for the Vespa series. And as you can see, if the two surrounding atoms are connected with the central atom, you have two electron groups, and the molecular geometry will be linear. So if those two surrounding atoms are the same, so the bonds are the bonds are going to be the same, and the bonds are polar. As assume this one will be slightly positive, this one will be slightly negative. So now you have a polarity arrow pointing from here to here. Same thing, this one is slightly positive, slightly negative. Now you have this polarity arrow pointing that way. As you can see, this is a linear, and these two will end up cancel each other out, because if you have two identical surrounding atoms, and this the net polarity of the molecule and it turns out this molecule assumed with the two electron group, as in this way, is AB2E0, will have the property of non-polar molecule. Okay. However, word of caution: if those two surrounding atoms are not the same, this goes out of the window. Then you'll have to draw the arrows to really get a good handle on that. And case in point, I'll give you a couple of examples. If I have a carbon dioxide, and now you'll have the Lewis structure of molecular geometry. According to this, you will be linear, and now you'll have the exact situation. They are pulling out opposite to each other, cancel each other out. So the whole molecule is non-polar. However, if you're looking at the molecule hydrogen cyanide, and I'm going to say the steps it goes through, and you will have a molecular geometry like this. It's a linear molecule. However, when you take a look at what is the polarity arrow, carbon has a lower electronegativity than nitrogen, so it's slightly positive. So now from here between the carbon and nitrogen, the polarity should go from the carbon to the nitrogen. However, now then if you compare the electronegativity between hydrogen and the carbon, hydrogen has a lower electronegativity, so then you will have a polarity arrow pointing this way. So now you realize actually these two arrows is pointing into the same direction. They actually reinforce with each other, and then this one will have a net polarity. So the whole molecule will be polar. And this molecule is very polar molecule. So please do not make the generalization. You see the AB2E0 will automatically give you the nonpolar molecules. Only under the condition the surrounding atoms are the same, and that statement would be true. If any of the surrounding atoms is not the same, and most likely it will be a polar molecule. It will be a polar molecule. So now take a look at 3 electron groups, and now you have this familiar shape if we do not have any lone pairs on a central atom. So this is AB3E0, and the molecular geometry will be trigonal. It means on the plane of this display surface, these 3 surrounding central atoms are on it, and this is this is also an equilateral triangle. It's an equilateral triangle. But if you say I have the surrounding atoms are identical, if I have a polar arrow pointing this way, and I have another polar arrow pointing that way, and I have the polar arrow pointing this way. So now you actually have to recall some of your geometry, the knowledge you learned in the geometry. Those are vectors. You can actually break them down further by dissecting them using a coordinate system. As you can see, I have arrow pointing this way. I have 2 arrows pointing kind of sideways, but they push them down. So the components for those 2, you will add it up. You will have, I'll change the color. You will have this vector. The components you projected onto the x-axis will cancel each other out because of the same magnitude but opposite to each other. However, now you will see here the downward arrow will be totally balanced out by the upward arrow. So as a whole, if we have AB3, E0 would be being the same for all of 3. And you will have this molecule to be nonpolar. Okay? Even though each individual bond can be highly polar, but the net polarity will be 0 because they cancel each other out. Case in point will be boron trifluoride. Remember, this is an exception to the octet rule. It's deficient. It's short of 8. But this was discussed in the previous podcasts. So let's just quickly go through that. That will be the Lewis structure. This one will be the Lewis structure, and the boron has only 6 valence electrons, but it's trapped. It cannot form a double bond. So this will be AB3E0, and the shape of this molecule will be exactly as shown here on the simulation. So it will be trigonal planar. Okay. So we also have 3 electron groups now, and you will have a lone pair. I strongly advise you to run the Colorado simulation program side by side with this podcast, so you can jump back and forth between those programs. Take a look at it. Take a look at it in the simulation program, and you can actually rotate the shape. You can actually rotate the whole molecule and take a good understanding about 3-dimensional shapes. So case in point, give you the case, it will be the sulfur dioxide molecule. As you can see, one of the resonance structure will have sulfur with a lone pair on it, one double bond with oxygen, and the other one with a single bond with oxygen. Or this one can assume more than 8 valence electrons, called expanded. It's called expanded octet. So you can actually form a double bond, second double bond. However, those details do not alter the AB2E1 notation for this particular molecule. So I have a lone pair on here. So now instead of a linear structure, now these two bonds has to be bending towards each other to accommodate this lone pair. As you can see, if we have an polarity arrow pointing to this way, and now you'll have the components going horizontal, they cancel each other out because they're perfectly opposing each other. However, the forces as components pointing downwards now, like this, that will be the overall sum for those two. Nothing is going to balance that, because this lone pair belongs to nitrogen, does not contribute to the polarity. So as we can see here, if we have, this is what we call the bent geometry, it will result in a polar molecule if individual bond, it's two individual bonds are polar. So now let's look at the 4 electron groups. Look at the 4 electron groups. And as we know it is, we call it the tetrahedral. Now we are in the 3-dimensional space. You can see this atom and the central atom is residing on the plane of the screen, and this one is actually pointing towards away from the plane of the screen, and this one is also does the same thing, pointing backwards, and now this one is actually pointing forward. As you can tell, the ball gets slightly larger, and this is going to be an even more challenging one if we have the 4 surrounding atoms to be exactly the same, and so now the bond is produced will be exactly the same. So now you can actually have all this if we have that, and if we have that, and also we're going to have that. Okay, so this is also going to have that, and now you see the 3 bond, the polarity is pointing downwards. It's pointing downwards. Take that section and add all of them up. You will be the same as this. Okay, it will be the same as this polarity, and then they was looking at the projection onto the x plane, and that will be equilateral triangle. Remember the 3 electron group with all of those linked with atoms, and they cancel each other out, so there will be 0. So if it's a tetrahedral and the surrounding atoms are the same, and you're going to have a non-polar molecule. And it is very important for you to know when individual bonds are formed, and individual bonds are very polar. However, but when you add them up into molecules, things could get interesting. Okay, things could get interesting. Let's take a look at a couple of examples. One of the examples I will use is carbon tetrafluoride, and you will know the Lewis structure will be carbon, fluorine, fluorine, fluorine. Okay, so there will be the AP4, so you'll have the tetrahedral shape. and this is exactly the representing one. So then this particular CF4 molecule will be nonpolar, which means it does not have any partial charge separation. However, at CM4, four of surrounding atoms, now the equation changed, and you will have CHCl3. Carbon is still in the middle, so carbon is still in the middle. H, Cl, Cl, Cl. So this is the proper Lewis structure for this particular compound. And you can see, go through the process, you'll notice you still also have to face okay. So now you start noticing when I have to draw the polarity arrow, and for chlorines is all from the carbon to chlorine. However, because the hydrogen has a lower electronegativity, so now the arrow for this particular one bond will be pointing downwards. So now you'll not only have this 3 polarity pulling downwards, now you have additional help from the top. So then this is by no means is nonpolar. So hence this one is actually polar. So this one actually is a polar molecule. Okay, so the key lesson learned here is do not take it for granted, do not generalize that. So it's quite different if you have a CF4 and full of the carbon, the full of the elements are connected to the carbon directly, and they are all the same. So that's why the symmetry works, and also it's a nonpolar molecule. But then when you switch to CHCl3, and then this one will give you the one. You have to look at the details. You know, as I always said, kind of the devil is in the detail. So in this case, the CHCl3 will be a highly polar molecule. So now just to continue discussion on the 4 electron groups, you will have this shape. 3 are connected with atoms, but now you'll have a lone pair on the central atom, and this gives you the trigonal pyramid shapes because of the repulsion for the lone pair of valence electrons on the central atom. So this is actually called the trigonal pyramid. It forms a pyramid and has a triangle base. So the ones now you start looking at the polarity arrow. So if you have someone pointing like this, and this is following that, and this is following that, as you can see, they all have the components pointing downwards and also horizontally. Horizontally, you can actually see it's the equilateral triangle. But however, when you have all this arrow pointing downwards, there's not much to balance on the top. So in this one trigonal pyramid, and if the surrounding atoms are the same, or even they are not the same, you will have net polarity for the whole molecule. So the whole molecule will be polar, provided individual bonds are polar. So when you have two lone pairs of electrons on the central atom, and now the whole shape is bent. And this is also the famous shape of water. Now you go through the motion, and you can still see if you have the polarity arrows this time are kind of like to draw it away from the central atom. They cannot possibly cancel each other out. So the bent molecular geometry, the molecule is polar. So now let's take a look at the 5 electron groups. If you have the 5 electron groups all connected with the surrounding atom, you will have this picture. As you can see, this is an equilateral triangle. You have 2 of them going perpendicular through them. And if we have the polarities, if all the surrounding atoms are the same, hence each individual bond, the polarity between them, it's the same. So if you're looking at those 3, they will cancel each other out, and now you have a net zero on this plane, and you will have one up, one down. If the surrounding atoms are all the same, and this is going to be 0. This is going to be 0 polarity. So the whole molecule is nonpolar. Okay, so the whole molecule is nonpolar. Case in point, SF6. Okay, SF6, you write everything out, you will have the same molecular geometry and the electron group geometry. Okay, so this one will, let's take a look at the others. So this is called trigonal bipyramid. The reason why it's called trigonal bipyramid is the base is trigonal. You can there are 2 pyramids, one on the top, one on the bottom. How about if one of the bonded atom is replaced by a lone pair, and this one is called seesaw, and some people call it some other names. But as you can see from here, this is equilateral triangle plane, and now we have, we can draw the polarity arrow this way, polarity arrow that way. So those 2 kind of pretty much cancel each other out, and now those 2 is pulling everything towards the left, and now you have a net polarity. So if individual bonds are polar, the whole molecule will be polar with this particular arrangement, spatial arrangement. So now if we take 2 electron groups, in this case 2 lone pairs on the central atom, now you will have a shape like that, and now you can see these 2 pretty much cancel each other out, one point out, the other one pointing in, and now if this is pointing out, nothing's going to be balancing this arrow. Those 2 pretty much cancel each other out. So in this one we'll have net polarity, and the whole molecule is polar. So it's called T-shaped molecular geometry. And now looking at this, when all the three pairs are kind of temporarily replaced, and now this is the shape. It's not bent. Actually, it should be linear, and this is a mistake. It's not bent. It should be linear. You can see if I draw the polarity arrow, oh, that's just not that great. Gotta erase it and redraw it. Just excuse my bad penmanship. And now you can see these 2 are exactly 180 degrees, and they cancel each other out. So the net polarity of the molecule is 0, and you will say the whole molecule is non-polar. polar, will be non-polar. And we can see some examples of that. One of the seesaw one will be SF4. You can double check on that, and then there will be a polar molecule, and ClF3. It will be the ClF3 will have the T-shaped molecule, and each individual bond is polar, but one of them cannot be cancelled. So the one molecule is also polar. So now we have the linear ones. We can have the CF2 xenon difluoride. Actually, it turns out this molecule is non-polar because the molecular geometry is linear, as we have here. So we're done with the 5 electron groups. And now take a look at the 6 electron groups. The first one come to mind will be the SF6, and you will have this particular molecular geometry is called octahedron. And that's why we call it octahedron. But now you're looking at, just remember, this shape is a perfect square, and these two are kind of it's got a stick going right through it. So if all the surrounding atoms are the same, let's hypothetically say they're drawing from there, this polarity will be cancelled by that one, and now you see this polarity will be exactly cancelled by this one, and this polarity will be exactly cancel each other out. So for the SF6, it turns out actually it's a non-polar molecule. Okay, non-polar molecule, because the individual bond cancel each other out. But that's provided all the 6 surrounding atoms are identical. If any one of them is not the same, and this is going to go out of the window. So if you can see, the net polarity for SF6 is 0, and the whole molecule is non-polar. But stay with the 6 electron groups. And now you can have is one lone pair sitting on here, and all the others, and this is going to form what we call it square pyramid. This is a pyramid, and this is a square. This is a pyramid, this is a square. Same thing, if all the surrounding atoms are the same, we can start drawing the net polarity arrow, and you can see roughly this two and this two can cancel each other out. As later on you're going to learn, this is going to occupy a bigger space, so the bond angle is slightly less than 90, but the differences are so small. But however, on this one, and if you're still pointing the polarity, it's still pointing this way, and now there's nothing to balance this. So because this is a lone pair, this lone pair belongs to the central atom. And if you have a square pyramid geometry and all the bonds are polar, and this whole molecule will be polar. Okay, the case in point will be the IF5. Will be the I in the middle, F surrounding it. 1, 2, 3, 4, 5 is all those valence electrons. And you also have a pair of electrons right sitting on the iodine, and this is exactly the case portrayed here. So the other one will have 2 lone pairs, and now you can actually looking at those four is actually on a square planar phase. So this is actually called a square planar. If actually we can draw the polarity arrow, this two cancels, this two cancels. So the net polarity for this square planar geometry will be 0. So the whole molecule will be non-polar. Okay, the whole molecule will be non-polar. Case in point, if you want to know the example, we have xenon tetrafluoride. You can write it out. It actually fits into the AB4E2 notation or the class. So, and now I would like you to take a look at some examples, and I will set up the website, and the link to the website. I'd like you to see the website. So let's continue with look at this website. The link is right on the top, and you have to activate run the JavaScript on here. And one of the things is very interesting. You can see the molecular shape. You can actually let it spin. Okay, so as you can see, the polarity cancel each other out, and for carbon dioxide, in this case, net zero polarity, so it has to be non-polar, and that's for linear for two electron groups. So now we can have for 3 electron groups if you do not have any of the lone pair. So if you can see like that, that's a trigonoplanar. It gives you the examples right over here, and it's highly symmetrical. And the polarity you have, provided the surrounding atoms are identical, will be 0. Okay, so now if you have a lone pair on the central atom, so now will be the AB2E1 notation, and now you can see it is a band. Shape. It is a band shape because of a lone pair on the central atom that pushes those two down, as you can see later on. As you can see, the bonding angle between those two bonds would be slightly less than 120. So you can actually let it spin. And now we look moving into the 4 electron groups. You can see the AX4, let it spin. You can clearly see these tetrahedral corners, and there are 4 corners. So now it's highly symmetrical if all the surrounding atoms are the same, and the polarity of each individual bond will cancel each other out. So the net polarity for the molecule is 0. So the whole molecule will become a non-polar one. However, and that's based on the precondition, all the atoms in the molecule that are surrounding atoms are identical. However, if they are not, give you an example in the previous slides, actually the molecule becomes polar. And now if you're looking at when you have one lone pair, and now you're looking at what we call pyramid, a trigonal pyramid, and all this if individual bonds are polar, now you will have a net polarity. The molecule becomes polar. The molecule becomes polar. And this is the most important one we started this unit with. If we have the two lone pairs of electrons and the two connected bonds, in this case the water, and now you can see it is the bent shape of the water molecule, and this one is bent will result in net polarity of this compound. So when you have that, say like ammonia and H3, you will have net polarity. The whole molecule is polar. And as you can see, if we have a trigonal bipyramid, AX55 of them linked together, as you can see, this is trigonal planar, and this is the 2 points, kind of the stick going through it. Here is a detailed example for that. And now if you have one of them is lone pair, and we just lose one here, and this is called seesaw. It's called the seesaw. And now you have two of them now, and then you can have, this is what I call a T shape. Two of them now, forcing these lines up. I'll give you the example, ClF3. So then when you have 3 of those are, backtrack on that, as you can see it's a T, it definitely will have a net polarity if some of the bonds are polar. But if you have 3 lone pairs of valence electrons, now you're going to squeeze everything into this linear shape, and now if the surrounding atoms are the same, you have them cancel each other out perfectly. So the end will be likely non-polar molecules. And now I switch gear to the 6. As you can see, you can let them spin, you can move them and manipulate them, have a good sense of 3-dimensional space. And now you can see it's highly symmetrical. They can cancel each other out. If all the surrounding atoms are the same, the net polarity of the molecule will be 0. Once again, if you have a polar bond in this particular geometry, most likely you'll end up with a non-polar molecule. So if you're missing one link and replace that with the lone pair, this is what you get. It's got slightly square pyramidal, and if those bonds are non-polar, if those bonds are polar, the whole molecule is polar, because the one was up there for this connection, so the polarity can now be balanced out. And the last one you want to see is the sort of the AB42 total 6, and but it's going to be on a square planar. Any of molecules with this particular geometry, like the xenon tetrafluoride, will have their polarities cancel with each other perfectly. You will have net polarity. You will have net 0 polarity. The whole molecule will be non-polar. Okay, so with that, we wrap up the molecular polarity vodcast, and please refer to the worksheets for further exercise. Thank you very much for your attention.